The recent commercialization of drone technology has introduced a whole new field of opportunity to use the powerful photographic capabilities of these versatile machines in order to analyze real world locations and objects from formerly unreachable angles. A general lack of knowledge and education from this field in the public sector ignited the spark to the development of High Five. High Five is a video and image analysis platform designed to integrate the complexities of drone technology with more common devices. While the system does offer a set of default analysis options, such as car and person counting, the main focus of High Five is in allowing users to develop their own analysis tools, giving them the power to analyze whatever they want and in whatever way they prefer. Over to you, John Ray.
On the screen, we find ourselves in High Five's website. From our landing page, you can navigate to any of our other screens and invoke our basic use cases, such as uploading images or videos. We've already uploaded a few videos and images for this demo. Before we demonstrate analysis, we'd like to give you a brief explanation on how this works. Hannes will now explain this.
The most basic building block for an analysis process is what we call a tool. There are two types of tools we use in our system, namely analysis tools and drawing tools. An analysis tool is a program that interfaces with a neural network and processes some input media, either image or video, through the model's classification. The analysis tool then makes use of a powerful and highly customizable metadata container to store its results. This container can hold anything from pixel coordinates of identified objects to the number of objects identified in a frame to the percentage each object matches the target classification. The possibilities are endless. Each tool can save different results to the metadata container, and this metadata is then passed on to each successive analysis tool in the pipeline until it finally reaches the specified drawing tool at the end of the pipeline. Here, the drawing tool will extract all the information stored in the metadata object and alter the frame in whatever means specified. Whether this means drawing boxes across identified objects or writing text to the image indicating an object count. High5 offers a set of default tools that any user can access and use upon logging in with their own account. We wrote all of the default tools ourselves. This includes the pre-processing and post-processing of each frame, in addition to using a pre-trained neural network model. The default analysis tools have self-explanatory names, and our box drawing tool simply draws red boxes onto the raw frame where the analysis tools identified appropriate objects.
Now that you have a better understanding of the analysis process, we've used our already created pipeline that identifies vehicles to analyze the already uploaded video. And this is the result thereof. We now want to create a pipeline that contains more analysis tools than just the vehicle recognition tool in our pre-existing pipeline. In our case, we'd like to be able to identify both people and vehicles. It is important to note that any amount of analysis tools can be present in the set of tools of the pipeline. However, a drawing tool must be present at the end of the set of tools. Now that the new vehicle and people recognition pipeline has been created, we'll start the process to analyze the already uploaded video, but this time with the newly created pipeline that contains more than just one analysis tool. Marco will now go into more depth on how the pipelines work.
Thank you, John Ray. When creating a pipeline, a user can add any number of analysis tools in any order before ending the pipeline with a single drawing tool. Once our pipe is constructed, it is ready to receive some media as input and begin processing. The provided media will start its journey by entering the pipeline at the first tool. The tool will test the media against its neural network and store whatever results the drawing tool will need into the metadata object. Both the metadata and media are then passed on to the next tool where this process is repeated. This continues until the final drawing tool is reached. Here, the drawing tool will consume the data stored by each analysis tool in the metadata object and project these desired changes onto the raw image through whatever functionality the drawing tool offered. The altered media is then returned as output from the pipeline and the analysis is done. We'll now head back to our web app and view the video we analyzed earlier. Where the former video only counted vehicles, here you can see both people and vehicles being counted by our new pipeline. This video was analyzed with High5's default tools, but our system's extensibility does not stop there. Our built-in tools are classified as default tools because we grant the power to the user to write their very own tools. This is primarily accomplished via the High5 Software Development Kit, or SDK. Our SDK is a freely available NuGet package, an importable library of sorts, which offers a simple yet highly customizable interface to write custom analysis and drawing tools. We'll only be giving a conceptual presentation of tool creation in this demo. However, our web app does have a link to a video tutorial explaining the technical steps to this process. To write your own tool, you'll have to import the High5 SDK into your project, where you can easily overwrite our interfaces to build either an analysis or drawing tool. If you do the former, you'll naturally be using your own neural network. The collection of your source code and model, if required, is then uploaded in unison to our system and stored as a single tool. However, for security purposes, you cannot immediately use your uploaded tool, as it is marked as pending for review. An admin user will first log on, review that your tool adheres to our constraints and does not contain anything malicious, and approve it. Once your user-written tool is approved, it can seamlessly be integrated into any pipeline as demonstrated earlier, giving you full control over what you want to analyze, how you want to do it, and how you want it represented. Here are a few outputs from our custom user-uploaded tools that we analyzed earlier. This street scene was run through a image segmentation pipeline that produced this output. Here you can see Hannes, one of our team members, and this image was pushed through a biological gender estimation tool which successfully identified him as a male. This is an image of a model which was pushed through an age estimation tool that accurately estimated her age as 23. These are only a few examples of the custom tools you can write and implement in our system. Before we practically demonstrate this, Hannes will give you an idea of the complexities behind our analysis engine.
Thank you, Marco. The analysis engine is the heart of the High5 project. As the name suggests, it handles the analysis of footage taken by the drone. Using the pipe filter pattern, it takes an image or a video as input from cloud storage and sends it through a user-created pipeline of tools to analyze the footage. The analyzed footage is then sent back to the cloud storage. Since we allow the user to construct a pipeline dynamically, we use factories and builders to create the pipeline. This pipeline is constructed at runtime when the user requires it. The construction is also responsible for putting each filter in the pipeline in its own separate thread, with concurrent queues as the pipes between the filters. The pipeline then has a source where frames are added to the start of the pipeline and a drain where analyzed images are fetched to encode them again. As you can see, the analysis engine has quite a complex design. We wanted to make it as modular and extensible as possible. Everything in the analysis engine is managed by this manager class. Now that I have discussed the analysis engine as a whole, let's talk about the individual tools specifically. We use convolutional neural networks in all our models since they are very effective for image analysis. We also have drawing tools that use the output of the analysis tool to draw the output onto the raw image frames before they finally get encoded and sent back to storage. The analysis tool itself does analysis using a pre-trained ONNX model found in the ONNX Model Zoo. ONNX, also known as the Open Neural Network Exchange, is a standardized format used to represent neural networks. This format allows us and the users of our system to easily use neural network models to analyze media. ONNX has good support in .NET and is good for performing inference using hardware acceleration. Onyx models also have better performance than TensorFlow models when it comes to inference. These models are stored using the .onnx extension. The Onyx neural network model is the only part of the analysis tool we do not write ourselves. We did have to implement all of the pre-processing and post-processing to give the model the correct input and process the output of the model. In order to increase throughput of our default tools, we make use of GPU hardware acceleration. The Onyx runtime allowed us to use CUDA cores to hardware accelerate the tools, allowing them to run up to 10 times faster compared to just running them on the CPU. Our biggest struggle with the analysis engine was making the throughput of the pipelines as high as possible. To increase our throughput, we used Onyx models that run efficiently and that can utilize hardware acceleration. We also needed to take as little time possible with the pre-processing and post-processing of each frame. We made use of lower level memory accesses and concurrency within our default tools to improve the throughput. On this slide, you can see some code where we made use of parallel for loops in our pre-processing of an image frame. The encoding, decoding, and every tool inside the analysis engine run in parallel on separate threads to improve throughput. Now we will demonstrate our whole system in action.
In this scenario, a farmer would like to count his cattle, and to fulfill this need, will use the High5 system. Using the High5 mobile application, the farmer will take control over the drone, and once in control, the farmer may now fly his drone and position it towards his cattle of which he would like to begin recording. The farmer may now record his cattle, taking care not to disturb them with the drone while he records. Once this footage has been captured, it is copied from the SD card of the drone, uploaded to the High5 websites, and using a custom cattle counting tool may begin analyzing footage of his cattle.
We'll now hop back to our web app where we can see the video of cows that Kyle uploaded that was taken by the drone. We're going to upload our own tool to count these cattle. To do that, we'll select our user profile icon in the top right and navigate over to the Uploaded Tools tab. Here you can see all of High5's default tools as well as your own uploaded tools if you have any. As you can see, we've already uploaded a counting cattle tool. However, it is waiting to be reviewed by an admin. Since this account is already an admin user, we can simply navigate to the Unapproved Tools tab and see our uploaded tools. You can then either download the model or the source code to check that the files aren't malicious. If they are, you can reject this tool, which will completely delete it from our backend, but we'll just go ahead and approve it. If you head over to your pipelines page, you'll now see that your custom tool is listed below High5's default tools. We'll now create a pipeline with our own user tool, the cattle counter, and the default box drawing tool to demonstrate this effect in our analysis. While the video is being analyzed, Ruan will briefly discuss the architecture of analysis request flows.
Let's have a look at how analysis fits into our architecture. While a good portion of our use cases are as simple as making requests from front-end to back-end, we found that our cloud hosting service did not offer us powerful enough hardware or sufficient processing power to efficiently run our analysis. We decided to switch to a microservice-based architecture to allow us to deploy multiple analysis engines to handle the various expensive processes. We deployed these to our personal computers. Naturally, we required some service to forward and manage analysis requests. Since we didn't want to overburden our backend, which was already processing most of the web client's requests, we introduced an intermediate WebSocket server that we call the broker. Once a user makes an analysis request from the web client, it is sent to our backend via a WebSocket to ensure the connection does not close prematurely, since analysis of large files can take quite some time. The backend then forwards this request to the broker through another WebSocket connection. This allows the backend to efficiently continue executing other requests while it awaits the analysis result. The broker will then determine which analysis server is currently under the least load and deliver the analysis request to the selected server using Apache Kafka. Inside the engine, the required media is fetched directly from blob storage, and the analysis process, as described earlier, will take place. The processed media is then uploaded back to the blob storage, and a notification is sent back up the WebSocket chain to notify the user that the analysis is complete. Now let's have a look at the result of the analysis we started earlier.
Here you can see the video the farmer uploaded of his cattle, successfully analyzed by our custom tool, fulfilling our user story. Finally, Carl will discuss and demonstrate our final wow factor, live streaming.
I will now practically demonstrate this wow feature in action.
What you're seeing now is the BDP Solutions team in our office, and this is the end of our demo.